Uh, Hello student, today I am going to teach you about the master's method. Master's method is the very famous and techniques that is used to derive the complexity of the recurrence relations. Master theorem is very much popular because this gives you the solutions in a very simple steps, easy way, and you do not need to construct the complete corresponding recursion tree and add on all the complex cost at each level, but in spite of that you take the look of the formula, and by deciding the particular case you write down the corresponding solutions. But there are certain conditions that you must know that where you can apply the master's method, because this method cannot be applied everywhere. The master methods can be applied only on the recurrence relation that are of the form Tn is equals to Atn by b plus Fn. If the recurrence relation is in this form, then only we can apply the master's method. In master's method, the where here there are a input problem that is of n size. The input is of size n, and we are dividing that problem into a number of sub problem, and each sub problem is of size n by b plus fn. Here a and b should be greater than 1, means that the number of problem and the fraction should be greater than 1, and Fn is the cost of dividing the major problem into smaller subproblems or smaller segments. If this condition holds, then only we can apply the master's method, otherwise we can't. And in master method, as I've told you, we directly derive the solution or solution, but how this works, for that we should know that how this has been derived. For the master's method, a problem that is of size fn is divided into the a number of segments, and each segment is of size n by b. Here, the problem of size n is being divided into n by c size a problem. That may sound some uh, odd, that if you are dividing n by b problem, then there should be b number of problems, but it happens in the algorithms. Then there are a number of n by b problems, and cost of dividing that sub problem is equals to fn, that is written at the root level. Now, the same way, we shall divide the problem of the size fn by b into the a number of segment, and each segment of is will be of the size n by b square, means n by b upon b. And at the level 1, where we are dividing the problem of size n by b, the total cost would be a times the cost of dividing the problem of size fn by b. So the total cost at level 1 would be equals to a into fn by b. And similarly at the level 2, the problem each problem will be divided into a segments. So there are a problem at level 1, and each has been divided into a for segments. So total segments at level 2 will be equals to a square. So the total cost would be equals to a square into f of n by b square. And this way we shall keep on dividing the problem. But how long can we can divide something? We can divide a thing entity only when its size reaches up to a value 1, because when the size become 1, we are not allowed to take a or b less than 1. So we cannot divide it further, because in the master's method the initial condition was that a and b should be greater than 1, and if a thing comes at the unit level, then we cannot divide. So the procedure will end at the point when we are left with a single entity. So this tree will end at the position when the problem size becomes equals to 1. So how long will be the length? How long will be this recurrence tree, or what will be the length of this recurrence tree? Definitely there are n number of element initially, and each level we are dividing it by b. means we are dividing a fraction of it by b, then this will each time that is being divided, so the total height would be log n base b, because in this way, because at the point when n upon b raised to the power h minus 1 equals to 1, when n and b raised to the power h become equal, then value of n upon b raised to the power k, where k is the length of the, suppose it is h, would be equals to 1. At that point it will stop. When n upon b raised to the power h become equals to 1, then at that point this tree will stop. So n is equal to b raised to the power h, and taking log base b on both sides, we can say that the height would be equals to log of n base b, right? And similarly, so the tree will be of length log n base b, and at root, and we can check out the case cost of division at each level. At initial level it is fn, at level 1 it is a fn by b, at level 2 it is a square fn by b square, and this tree is of length h. Then h is equals to log n base b. So at the n base b, or we can say that the h is equal to log bn. So each level this will be equals to T1, the problem will be of size 1, and here we can say that a raised to the power log a raised to, the height is, number of segment would be a raised to the power h, and h is equals to log n base b, and we know through the mathematics then that we can write n raised to the power log a base b is equivalent to log a raised to the power log h base n base b, because in the right two portion n and a can swap with each other. At the lead level, n raised to the power log a base b is equals to a raised to the power log n base b. So that would cause the height. So we can write it as n raised to the power log a base b into t1. This will be the cost at the leaf node. So here I have shown this in the diagram. The leaf is equal to a raised to the power h, and we have found that the height is equals to log n base b. Using the simple logarithmic equation, we can write a raised to the power log n base b is equals to n raised to the power log a base b. So that will be total cost. So why we have done, because in this tree the number of sub problem and number of leaves, we shall establish a equation, and depending upon their equations and size we shall decide the different cases. For example, there could be two possibilities, that the number of leaf nodes and the number of leaf nodes and the cost of division. If we compare fn in each case, we decide that in which case the particular master theorem will lie depends upon the two variables fn and n raised to the power log a base b. Here we shall compare these two. In case 1, the fn n raised to the power log a base b, or the number of the leaves, exceed the cost of the division at root nodes. So this can be written as fn is equals to O of n raised to the power log a base b minus epsilon. If something is greater than that, after deducting something, you are equating that things. So n raised to the power log a base b is greater than fn. Simply we can say that, or we can say that fn n raised to the power log a base b grows polynomially larger than the terms fn, or fn is grows polynomially slower than the n raised to the power log a base b. Then the questions comes under the category 1. In that situation, if the problems comes under the category 1, then Tn is determined by the dominating term, that is the n raised to the power log a base b, and the final complexity would be equals to theta of n raised to the power log a base b. We can say that the complexity would be equals to the number of leaves, how many problems you are dividing, right? In case 1, what happens? In case 1, the weight increases geometrically from the root to the leaves. the leaves holds a constant fraction of the total weight. In this means the cost is determined by the leaves because they are the dominating terms, and and the weight of this tree increases when we keep on dividing the tree. So in this case, the cost would be determined by the number of the weight of at the leaf nodes, that is equals to n raised to the power log a base b. So this is the situation in case 1. The complexity of the equation would be equals to n raised to the power log a base b, because in this case most of the weight increases at the leaf sides. Now in the case 2, as I've told you, case is decided on the basis of the two variables fn and n raised to the power log a base b, and case 2 comes when these two functions grows equivalently. When means the growth of the function fn and the growth of the function n raised to the power log a base b increases with a similar rate. In that situation, the complexity of the equation would be equals to theta of n raised to the power log a base b into log of n. Ignore the term k plus 1 here. There is a normal constant, that is the base, you can consider it as the log n. So in general it is 2 log n. So when the both function grows with a similar rate, in that situation the complexity is equals to n raised to the power log a base b into log n. So this is the case 2. Now the case 3. In case 2, as I've told you, the weight is approximately same on at the each level. In the case 1, the weight was increasing at the with the increasing levels, and in the case of the second case 2, the load at the weight at each level are nearby equal. So in this case, the complexity is equals to n raised to log a base b into log n. Now we move towards the case 3. In case 3, fn is equals to n raised to the power log a base b plus epsilon, where epsilon is greater than 0. Here fn grows polynomially faster than the n raised to the log a base b. Or we can say that the fn is greater than n raised to the power log a base b. And which one is greater will decide the complexity. So here the complexity would be decided by the fn, and the complexity would be equals to theta of fn. But what point that you should keep in your mind, that the case 3 needs one extra verification, that is called the regularity condition. The regularity conditions means the terms a fn by b should be less than c fn. This condition is called the regularity condition, and this condition should be satisfied for the value of c that is less than 1. If conditions holds, then only we can apply case 3, and otherwise we cannot apply the case 3. So keep in mind, when fn is greater than n raised to log a base b, you have to check the regularity condition, and after getting that the regularity condition is satisfied for c less than 1, then only you should apply the case 3 solution. And in this situation, the complexity of the equation would be equals to theta of fn, right? Uh, in case 3, the weight decreases geometrically from the root to the leaf nodes. The root holds a constant fraction of the weight. Means the inside, in this case, this is just opposite to the of the case 1. Here the n raised to the power log a base b is less than fn, and in case 1, n raised to the power log a base b was greater than fn. So these are opposite to each other. In that case 1, the weight was increasing with the increasing level, and here the weight decreases with the increasing levels. So in this case, the complexity would be equals to theta of fn. Now we shall discuss some of the example of all these cases to understand all the problems. Here Tn is equals to 4Tn by 2 plus n. Here A is equals to 4 and B is equals to 2. So we shall determine the two variable n raised to the power log a base b and fn. So n raised to the power log a base b would be equals to A is equals to 4 and b is equals to 2. So that would be equals to n square and fn is equals to n. So here fn and fn is equal to n and n raised to power log a base b is equal to n square. So we can clearly say that n raised to power log a base b is greater than fn. So in this situation, that complexity would be decided by the n raised to power log a base b, and Tn is will be equals to theta of n square. And in next example, Tn is equals to 4Tn by 2 plus n square. Here in this problem, a is equals to 4 and b is equals to 2, because this problem is very much similar to the last problem, but here fn is equal to n square, whereas in the first problem it was n. So here n raised to power log a base would be equals to n square and fn is equals to n square. So in this case, when both are equal to each other, means both rows equivalent with similar rate, then fn would be equals to n raised to power log a base b into log n. So here the complexity Tn would be equals to n square of log n. Now the third example. Here in this question, the question is same, Tn equal to 4Tn by, but the Fn part is changed. Now it is equals to n cube. So in this situation, n raised to power log a base b would be remain same. That is equals to n square and Fn is equal to n cube. So in this case, we can say that Fn is equals to n square plus epsilon. Definitely Fn is greater than the n raised to power log a plus b, log a b, log a base b, for epsilon is equals to 1. So we shall check and make sure that this either it lies under the case 3 or not. For that, we have to check the regularity condition. The regularity condition is a fn by b should be less than c of fn. Means here in this question, we know the value of a and b. So in this question, b is equals to 2. So in putting the value in this equation, a is equals to, here a is equals to 4. So a fn by b means 4 of fn by 2. 4 of fn by 2 should be less than equals to c of fn, means fn by b, fn by 2, n by 2. Here fn is equals to n cube, fn is equals to n cube. So fn by 2 cube, fn by 2 is equals to n by 2 cube. Then n by 2 cube will be equals to n cube by 8. So a is equals to 4, 4 n cube by 8 means n cube by 2 should be less than c of fn, means n cube. N cube and n cube will be cancelled out. So we can get that c value should be less than or greater than or equal to 1 by 2. So here we can say that the value of c lies in between 1 by is equal to so 1 by 2. So this satisfies the regularity condition, and so we can say that this question can be solved using the master theorem case 3. In master theorem case 3, according to that, the complexity would be equals to theta of n cube. So that would be equals to Tn would be equals to theta of n cube, right? Now the last question. Tn is equals to 4Tn by 2 plus n square of log n square by log n. Here in this question, fn part has changed. The n raised to power log a base would remain same, the n square, but fn is equals to n square by log n. Basically, I have told you that in this situation we shall check that regularity conditions holds or not. In regularity condition we check out that if the term fn is greater than n raised to the power log a base b, it is should be polynomially greater, and if it is polynomially greater then we can apply the case 3, and if it is not polynomially greater than the terms fn then we cannot apply the case 3. So in this case, when we check that the relation between fn and n raised to the power log a base b, we can do that by simply dividing the functions. Then we can say that they are 1 by log n of each other. Fn is 1 by log n of the term n raised to the power log a base b, means it is not related to the other term with in polynomial ratio. So in this case regularity condition will not cannot be satisfied, and then we can say that this question cannot be solved using the Master's theorem. So that's all. There is one point you should remember, that you cannot force that every recurrence problem can be solved using the Master's method. For example, in the example number 4, where the regularity condition failed, this question comes under the category where Master theorem cannot be applied. There is a gap between case 2 and case 3, and this question comes under that. Because of that, it is not polynomially it is greater than n raised to n raised to power log a base b is greater than fn, but it is not polynomially larger than that. So we cannot apply the Master's theorem over that. So this is the case. So now I summarize it once again. The Master's theorem is used to derive the complexity of the recurrence relation, which are in the form Tn is equal to Atn by b plus Fn, where a problem of size n is being divided into a number of subproblems of size n by b, and Fn is the cost of the division. And in this case, this a and b should be greater than 1. But means we cannot divide things after a single entity group. And in case 1, the height of the case 1, the weight shifts towards the leaf nodes, and the complexity is equals to n raised to the power log a base b. And in case 1, n raised to the power fn is equals to big O of n raised to the power log a base b minus epsilon. While in case 2, the both n raised to the power log a base b and fn are equal, and the complexity would be equals to n raised to the power log a base b into log of n. And in this, the weight is divided throughout nearly in same way throughout the tree. And in case 3, the weight decreases with increasing levels. So in this case, the total complexity would be equal to theta of fn. So these are the 3 cases, and in third case we should take extra care that regularity condition is being satisfied or not. Regularity condition is a fn by b should be less than c fn for the value of c smaller than 1 and between 0 and 1. So if the condition is satisfied, then only we can apply the case 3, and otherwise not. So we that's all about the Master's theorem. Thank you.